In this video, I'd like to take a look at two important related questions and what the latest research has to say about them. One, what are the mechanisms of transmission for COVID-19? And two, do masks of the different kinds work to stop this transmission? Watch the rest of the video for details, but to summarize here, first, on the point of transmission, the open question is coronavirus airborne? Now, this is outside the very specific context of aerosol generating hospital procedures. Like a lot of questions in literature about the size, duration, and distance of travel of droplets, there's a lot of gray area, a lot of variability in definitions. But airborne generally refers to long distance transmission of small droplets, aerosol droplets. So is coronavirus airborne? The answer is maybe. Proving this kind of thing, especially in real world context, is quite difficult because you have to show not only that virus gets aerosolized on small particles, you also have to show that these particles travel a long time and that they remain infectious. The related and perhaps more important question is whether face masks work to stop this transmission, both on the small aerosol droplets and the large droplets, and the three different kinds of masks, which are the N95 respirator masks, the surgical masks, and the homemade cloth masks. So, do masks work? The answer for the general public is yes. I cite some of the research here and discuss it through the rest of the presentation. But what do they work for? They work as source control, which is a technical term for saying they protect others from your infection. Now, zooming out from the individual at the society level, that's pushing towards a policy that everybody should wear masks. My mask protects you, your mask protects me. Now, that's currently looking especially at homemade cloth masks, but also at surgical masks once the supply loosen up. But it is not looking at N95 respirator masks, which should be used exclusively by healthcare workers to protect them as PPE, as personal protective equipment. The references here and the discussion in the rest of the video show why masks are effective as source control and why it's imperative that people should be wearing them. Specifically, that a huge percentage of the population, there's a lot of studies out there, but it's 18 to 50+% are asymptomatic or mildly symptomatic, meaning that you may not be aware that you're sick. So saying simply when you show symptoms you should be wearing a mask is not sufficient. Also, you're most infectious in the first week, which means that that very period where a lot of people, most people perhaps, are asymptomatic or mildly symptomatic, they're the most infectious. And finally, there's excellent research emerging showing that masks, surgical and homemade masks, work both to stop aerosol, small droplets, and respiratory droplets, large droplets. Okay, let's look at some key modes of transmission. First, I'd like to delineate between two types of particles, and I'll discuss the specifics of sizes and different definitions that people use later on. So first, aerosol, small droplets, also called droplet nuclei, are the ones that could be inhaled. They're inhalable. And then second is just called droplet or big droplets or respiratory droplets, are ones that come in contact directly with the mouth and nose, mucus, and moisture. I'd like to also separate it into four kinds of transmissions. So looking at aerosols, you can look at long range and short range. Long range, longer than 1 or 2 meters, 3 or 6 feet, is generally referred to as airborne. Short range is within that 1 or 2 meter range. For droplets, there is direct transmission and indirect transmission. So here's a quick terrible diagram I made where person A sneezes and there is big droplets that fly out of his mouth and small particles that are aerosols. Red is aerosol, blue is droplet. And as those particles fly out into the room, let's look at two people, B and C. B is within that short range of 1 or 2 meters, and C is farther away, maybe not even in the same room. And I label the particles in this diagram. Hopefully that's helpful. So one is the long-range aerosol is hitting person C, short-range aerosol and droplet transmission directly going into the exposed mouth or nose areas. And the indirect droplet transmission occurs when another person B here, comes in contact with that surface and then uses the hand to touch their face, to touch their nose, to touch their mouth. Here's a nice 3D model visualization. theoretical of how the different sized droplets spread through the room. The green and the yellow are the large droplets. The red is the aerosol small particles that spread through the room. And you see the green and yellow fall to the floor quickly within a certain limited range. And then the red cloud spreads throughout the room with some interesting biophysics of how the actual clouds move, some turbulence dynamics there. This particular paper suggests that effective ventilation is essential for dispersing the particles sufficiently so that they're not infectious. And obviously, in indoor environments, not having meetings of multiple people in the same room. So really basic practices of social distancing and physical distancing are still essential as one component of preventing transmission. So on this question of whether coronavirus is airborne, is it in fact transmitted through long-range aerosol droplets? One of the early studies was on a 48-seat bus in Hunan province, China, on January 22nd. A bus was traveling for 4 hours with one person shown here in red infected. And by the time they got off the bus, the people shown here in orange and blue also got infected. Now, the range there of 4.5 meters from the farthest passenger raises a question: is it airborne or not? The study suggests that perhaps it is airborne because of this kind of range. But to me, from reading this work, it's not clear that it cannot also be indirect droplet transmission, where the initial COVID carrier may have touched the seats and thereby allowing for indirect droplet transmission. Okay, let's talk about sizes. How big is this virus? It ranges, depending on the analysis, but 60 to 140 nanometers. Just in case you might not know, there is 1,000 millimeters in a meter, there is 1,000 microns in a millimeter, and there's 1,000 nanometers in a micron. And then below on the slides are the symbols usually used to designate millimeters, microns, and nanometers, with micron using the mu symbol, which makes it very difficult to tweet about. What about the size of particles that can carry these viruses? So there's a lot of variation in literature on this arbitrary cutoff between aerosols and droplets, droplet nuclei and respiratory droplets, but usually 5 to 10 micron is the cutoff point. So everything below that is an aerosol, everything above that is a droplet. The smaller the particle gets, the more likely it is to float in the air, and the more likely it is to be inhalable, and the deeper it goes down to the lungs. And just because viruses may be able to travel in aerosol particles, there's still open questions about what is the infectious dose. So what's the impact of the dose of the viral exposure? And also what's the effect of the duration of the exposure? There's some fascinating facts here, especially on the turbulent gas cloud dynamics. Basically, for a sneeze or cough, how far can certain kinds of droplets travel? And the kind of dynamics of clouds allows clouds of droplets to float in ways that you wouldn't expect, float very long distances. And there's research showing that it can travel, as opposed to the WHO and the CDC recommendations of 1 meter or 2 meters, it can in fact travel for 7 or 8 meters or 23 to 27 feet, especially for high velocity things like a sneeze or a cough. In general, as a side note, just the biophysics of droplet emission is not well understood. The more I've looked into this research, the more fascinated I became into the movement of gas clouds, of turbulent gas clouds, like wind in general. It's super interesting. In my main work of artificial intelligence, this comes up in really interesting ways for flight, for drones having to deal with wind, especially turbulent, unpredictable wind. It's fascinating. Okay, let's look at droplet counts. For sneezing, about 40,000 droplets are emitted. When you sneeze, when you cough, it's 3,000, and just talking, it's 600 droplets per minute. Now, in terms of indirect droplet-based transmission, there's a lot of variation in terms of surfaces, going from 5 days to just a few hours, depending on the surface, from metal to glass to wood to plastic to cardboard. So on the open question of is coronavirus airborne, there's been quite a few studies. I cite them here. Many studies say no, some say yes. So to me, the open question is, if you show in a study that short-range aerosol transmission is possible, does that indicate that long-range viral transmission of aerosol is also possible? The point is, we don't know, and the data is currently limited, both in the size of subject and either how connected it is to the real world or how controlled it is of a study. So from a scientific perspective And also from a policy perspective, what do we do? Well, there's a lot of lessons from history where they failed to be cautious and assume no. I think it is safe when there's uncertainty in this case is to assume yes. But luckily, studies are showing even for aerosols, masks work. And not just N95 respirator masks, but surgical masks and homemade masks. But this is a good place to say that day by day, new papers are coming out, new data is coming out. We're learning a lot of new things. I particularly like the quote from Charles Chapman, who's one of the seminal figures in the study of infectious disease from over a century ago. Science can never be a closed book. It is like a tree, ever growing, ever reaching new heights. Occasionally, the lower branches, no longer giving nourishment to the tree, fall off. We should not be ashamed to change our methods. Rather, we should be ashamed not to do so. I agree with this wholeheartedly. I think this applies to the WHO and the CDC. I think this applies to the individual scientists. I think this applies to questions of whether the virus is airborne and whether masks of the different types are able to slow the transmission of the virus. So, do masks work? There's two cases we want to make very explicit because there's a lot of confusion here. First case is source control. Second case is PPE, personal protective equipment. Source control means prevent me, if I'm infected, from spreading my infection to others. PPE means protect infection from others to being spread to me. And especially in the West, there's a connection between the question of do masks work with the connection do masks work for PPE, for personal protective equipment, to protect me from others. The key studies here and the power of masks comes from the first case of source control, of whether the mask can prevent me if I'm infected, especially in the case when I'm asymptomatic, which is a very large fraction of the population, from spreading that infection to others. This is where masks are essential for slowing the spread of the infection. Okay, so those are the two cases, source control and PPE. And then there's three types of masks. There's the homemade cloth masks, there's the surgical masks, and then the N95 respirator masks. Let's start with the last first. N95 respirator masks work when they're well fitted as personal protective equipment, and they're used by healthcare workers, so you should not buy them, especially because there's a severe shortage of them currently. So leave those for healthcare workers. Same goes until there's a surplus for surgical masks. So N95 respirator masks is yes for PPE and also for source control. Now, surgical masks, there's a recent excellent study shows that surgical masks work to stop both aerosol and respiratory droplets for the novel coronavirus. I describe this study in the next couple of slides, and there's other studies that show the effectiveness of surgical masks. The thing there's not a lot of studies of is the effectiveness of homemade cloth masks, but there is a strong study from 2013 looking at different materials and comparing them to the effectiveness of a surgical masks. Shows that a single layer of cotton, like a cotton t-shirt, has 73% filtration efficiency of a surgical mask. So they're not as good as surgical masks, but they still work. 73%, 70% is a huge reduction in transmission rate. Now let's zoom in on this study that came out just yesterday on whether masks are effective, and it looks at several viruses, including rhinovirus, influenza virus, and the coronavirus. And this is the interesting thing here is there's a lot of variability between the effectiveness of masks against these different kinds of viruses. Shown on this slide is the rhinovirus, which is the most common virus contributing to the common cold. And in the plot here, the two red boxes show the efficacy of the masks for stopping two different droplet sizes. On the left are droplet particles that are greater than 5 micron. So these are the respiratory large droplets. And on the right are the aerosol particles, the smaller ones, smaller than the 5 microns. And you see here that the masks for the rhinovirus are not very effective at filtering it. Now, if we look at the results for coronavirus, we see that, again, the two boxes here show the effectiveness of the mask for filtering the droplets of two different sizes, above 5 micron and below 5 micron. And what's shown here is that for all of the samples, the virus was completely filtered, both for aerosols and respiratory droplets. Okay, takeaways. What should healthcare workers do? They should wear N95 respirator masks, or in the worst case, surgical masks, as PPE, personal protective equipment. What should the general public do? We should all wear homemade masks, all of us, as source control until the supply of surgical masks exceeds the need of healthcare workers. And the question of, do masks work for general public and why? Yes, as I showed in the citations, they work to stop both the aerosol and droplet-based transmission as source control. That means my mask protects you and your mask protects me. That's, for many of us, a fundamental shift in perspective on our role in slowing this virus. I mean, we're in this together. That's the fundamental idea here, is in me wearing the masks, I'm helping protect the rest of the population, not myself. That's a shift in thinking that a lot of us need to take in order to help slow this virus. But I also think there's a powerful psychological signal that happens here when you wear a mask. By wearing a mask, you say that I care about your well-being in case I'm infected. And that allows us to regain trust and this fundamentally necessary cohesion that we need for society to function. So there's going to be a lot of skepticism, a lot of worry about whether other people are infected and so on. The masks will serve psychologically as a catalyst for us to be a community again, which is essential for an effective society and an effective economy. Speaking of which, for the capitalists watching, there's an excellent study from Yale, I believe, showing that every mask that is worn will generate $3,000 to $6,000 per capita due to the reduced mortality risk. And this doesn't incorporate the money lost by keeping the economy closed longer. So this is strictly about the reduced mortality risk. So there's a financial, moral, and epidemiological reason that we should all be wearing masks. Thanks for watching. Hope everyone is staying safe out there. Stay strong. We'll beat this thing. Love you all.